horizontal grid, basically in atmosphere and ocean, which is quite convenient with not too many vertical levels. But if you look at sort of like the performance of the model, this is shown here on the right side, and there's like some performance metrics against present-day reanalysis data for different variables like radiation, temperature, winds, and so on, compared to reanalysis data, and then compared to a lot of CMIP5 models in this case, where red means basically the model is performing worse than the ensemble mean, and blue means the model is performing better than the ensemble mean. You can see that the range of HCM3 simulations, HCM3 model versions that we use here in Bristol, they are not perfect, but they are also very well within the range of at least the CMIP5 range of other models in terms of global mean biases in the model. So it's reasonably good mean state in the model. And the real interesting thing for us is now, even though we have a good mean state, the computational costs of this model are very, very low in terms of modern day standards. So I just put this comparison here at the bottom in this table. So the version that we're using for the results I'm showing today is the HCM3 version with the UM in version 4.5. And this is something we can actually run just at our local HPC at the university and basically just use like a single node with only like 28 cores, but we still get roughly like 150 model years out of it per day. So that's a lot. So, and we can therefore means we can run dozens or hundreds of simulations in parallel with this, even on a local HPC system, which is great for exploring all sorts of uncertainties and transient changes. Just as a comparison, the other model, for example, that I'm currently using for paleoclimate application is it's called HEDGEM3, so like a newer version of our UK climate model, just a physical climate model core using UM 10.7. This is something then where we really need like national infrastructure to run this, and we, for example, like for a typical simulation, we need to throw probably like at least 2,000 cores at it, and then we only get 5 model years back per wall clock day. So this is like a factor of like 1,000 or 2,000 difference in terms of computational cost, which is obviously quite significant. But like I said, the mean state climate, at least compared to CMIP5 models there, is very, very good in this model, and therefore it allows us to explore a lot of different types of questions in the paleoclimate research. And one of these questions I wanted to present today is really climate change on geologic timescales over the whole, what we call the Phanerozoic, so the last 540 million years. And for this, basically, what we do is we take our present-day model and we more or less only change 3 boundary conditions, so to keep it as simple as possible. So we change the geography through time, so you can see the different time slices here shown as this animation. So we have roughly 1 simulation every 5 million years going back through time, and you can see sort of like this what we call like Minecraft type of resolution of the model. It's quite coarse, but it's also basically good representation of what we actually know about the paleogeographic reconstruction, because for most of the time periods, especially if you go to the early Phanerozoic, the uncertainties are huge. So we change the geography, we change the CO2, so we pick for each of those 100 time slices, we pick the CO2 level for this appropriate, for the associated stage, put this in the model, and we change the solar luminosity, which is sort of like we assume linearly increasing over these geologic time periods. And that's basically all we do, setting up the models. And then, yeah, we get basically a lot of results back. Models. So just looking at standard output of like potential temperature, salinities at the surface, both wind stress and winds as well. Just basically standard output that you're all familiar with, that we get from each model simulation, but you have to then multiply this by 100 or 1,000, depending on how many simulations we do there. So this basically gives us really a lot of data. So this is even a challenge for people who are really working with climate model data or model output every day. It's a lot of data to analyze. So the big question that we are facing at the moment is, how do we make this data accessible in the end, and especially accessible to other disciplines in paleoclimate research. So I try to show you that a lot of different disciplines are interested in using our model data as like a reference data for their own research. And people are not normally familiar with Python or processing on the command line, for example. So how can we provide them with meaningful access to our data? And one of the ideas that we came up with to at least make a start with this is the climatearchive.org platform. And the easiest description I can always give for this is sort of like the Google Earth for climate data, which is I call it. That's this sort of like the whole idea. Because if you go one step back, think about how do we normally access or share like large ensembles of model data, something like CMIP6, for example. Then we use the Earth System Grid Federation infrastructure there to store all of the data, like hundreds of different simulations times hundreds of different variables that we store there. And this is great for modeling experts to share the data, but it's really hard to access for most of our, at least paleoclimate community. And even if you are able to download these files, process them, they are still quite complex, like 2-dimensional or 3-dimensional geospatial data sets, and extracting like subsets of data that individual researchers are interested in is still quite complex task for a lot of us. So I think, at least for the latter question, accessing this data is actually something that we are in a way all used to do on more or less like a daily basis, whether it's using like GPS navigation or checking weather forecast or just flying to like your next holiday location here on Google Earth. We all interact with these large geospatial data sets every day, and it's we can access the underlying information that is relevant to us. The only difference I think there is that we are used to this super intuitive user interfaces, just flicking the globe in Google Earth or just dropping a marker there for a location that we're interested in, want to get more information. That's how we are used to interact with the data, and that's basically all the underlying idea of the Climate Archive platform is we take our model data, the standard NetCDF model data that we produce routinely with our climate model data, with our climate models, and we add this very intuitive virtual globe user interface to it that people know from everyday life. And with a bit of coding and a bit of a lot of patience from your line manager, basically, then you end up with something that looks like, I'm on the right side. And I think this looks much more like a sort of like Google Earth approach than what we had before. So the idea is we take the same data, we put it into this one consistent 3-dimensional environment, which is then available on the website. So the data on the left and the right is exactly the same, showing like a pre-industrial simulation. The idea is then we don't show like the full contour plot of the geography, but we just use this saturated relief plot on the right to indicate the vertical elevation. For example, for the circulation, we don't show these vector plots, but we just basically move these vectors around and scale them by the magnitude to just highlight important regions. And the same, for example, in precipitation and surface temperature, where we just highlight parts of the data set, which are then customizable by the user, but which allow us to basically compress several different layers of data into a single visualization to really show the complex interaction between different data sets, and also what I would argue like just the beauty of the underlying data that we produce. So just a very short look into like the technical implementation of this. So just for the nerds among you, basically, I just promised 2 slides, so don't worry. When we started with this, I wanted to really have like just a single-page website that is just running in the browser without needing to install any software or something. Basically, that you can just click a link on your smartphone and start playing with the data. It's really to have this access as without barriers, as easy as possible, to just allow people to just jump right into the data, start exploring this data, and have like an interactive access without any hurdles there. So for this, I want to have like a real-time environment, which basically means every change that you do on the screen is just immediately reflected on the display. So you don't have to click any sort of like make changes, click an update button or something like this. You really just want to start playing with the data, like something when you click a link to go to Google Earth, for example. It's the same approach. So for this, we need sort of like a 3D environment, which we can use a library for in the web, which is called 3JS, which is just providing sort of like this bare bone 3D environment, and the rest is basically up for us basically to think about how we can visualize then our model data in this 3D environment. But the idea is we define this sort of like scene with all of different meshes for different model layers. We put all of this into one big scene, put a camera somewhere, and then we take a render, which basically just takes like images 60 times per second of the whole scene, which gives this sort of like real-time visualization of our data. So this is I'm not the first person to think about this, obviously. So I just want to mention there are other alternatives doing this already. For example, like Cesium.js is a popular one using for geospatial data, 3D visualization on the web, and also a lot of people using like Blender for like offline rendering of like climate model output nowadays. So just like some other alternatives for this. It's just that I basically wanted to build something that's really custom for our climate and especially paleoclimate data. And the real trick there to make this as performant as possible, because like this really, the success of this really depends on how fluid this is, how easy it is to interact with the data, is to do basically all of the data processing on the GPU, so like the graphics card on your device, and this can even be like a smartphone, which is quite powerful GPUs nowadays, because we need to render these frames like 60 times per second. And if you think about just doing like a Python plot, for example, of like one global field of your model data, this can normally take longer than the 60th of a second. So we need to do put all of the workload basically onto the GPU, which is really great for the parallel processing. You can do a lot of things parallel, and then therefore we need to basically store all of the data, not NetCDF, which is not great for a browser, but into textures like PNG images, for example. And just one example is shown here at the bottom, showing like the global distribution of PFTs, so like plan functional types of our model with 3 different time slices. And this is basically what the software sees in the end. If you have more questions about this, happy to answer this after the presentation. But really, for the end of the talk, I just wanted to give you some sort of like impressions of the actual software and the platform. So this is all live at the moment, available at climatearchive.org. So depending on how many frames Zoom will allow to travel all the way to Australia, I don't know how it will look in the auditorium there. Otherwise, feel free to just visit the website on your own. Just a very brief look at the website. So this is basically what you get when you start. You see we build up the Earth, the present day Earth, with all of the different layers from our present day simulation, and you can just click the globe, zoom in and zoom out, whatever region you're interested in, and we can load more details basically once we go to a higher zoom level. We can have all of this in a 3-dimensional space, so we can change the projection like we want. We can just tilt the whole thing. So basically, we can just fly through our model data however we like, and look at specific areas of interest. We can select the different layers that are currently implemented. Obviously, we can add more and more of these layers over time. But the real idea is then at the bottom, we have this geologic timescale, which basically allows us to merge all of these 100 model simulations in time by using just naive linear interpolation at the moment. But the GPU can really basically compress everything and do like the interpolation more or less for free on the GPU. So it's quite convenient to do, and we can select individual time periods. For example, like a researcher interested in Cretaceous climate change and a specific region can just double-click anywhere to extract the underlying data from the nearest climate model simulation that we have available, and then compare this, for example, to different time periods, in this case, like the Eocene, and add all of this to some sort of like think about like a data cart or like a shopping trolley in a way, there of the data, compare different time periods, and then in the end export this data to something like a CSV file, which they import them to Excel, for example, to do some model data comparison. So this is like a very common workflow that we wanted to address there. And just one thing, we have like a lot of different applications. So we're not using this only for like paleoclimate, but for all sorts of time periods and planets, basically. So like I just put a couple of examples here. So on top left, the last 500 million years is basically what I showed just now in last 20 minutes. And pardon?
A couple of minutes to go.
Yep. Okay. Yeah. Nearly done. Thank you. So on the top right, we have, for example, we use the same engine to just look at future climate change, which is helpful to just visualize like two worlds side by side, like a 1.5 degree warming, 3 degree warming world. Let the user just explore these different scenarios and look how these global climate targets basically are reflected in local climate change signal, how different they are in different projections. And we also do like a lot of outreach activities, for example, using the again to simulate, for example, like the climate of Arrakis to just see whether people could survive there, or the Wheel of Time. And this is always very helpful to just explain to more people like how climate models work, how we adapt them for different time periods. And what I'm really excited about this project is that it has like the same engine, the same approach, has like application in a lot of different areas. So like I showed you the application in science to make our data accessible to scientists from other disciplines, for example. We really use it a lot for education. So like students really love to just get their hands basically on the actual data, play with different time periods, compare past, future climate change next to each other. It's very, very helpful for that. And also we do like a lot of outreach work by, for example, like building exhibitions for natural history museums and so on, where really interactive exhibits really help to people to get excited and engage actually with our model data in the end. So just as a summary and outlook, I can show. I hope I showed you that we can really use these older low-resolution models, which still have a reasonably good mean state climate, and the current computational resource that we have allows us then to perform like really large ensembles of parallel climate model simulations. So hundreds or even thousands of simulations in quasi-transient fashion, or like exploring parameter space. This is very, very helpful, and we're doing this with the HETCM3 climate model in Bristol. Producing all of this data basically motivated us to start developing this climate archive platform to really make all of this data, or at least some data of this subsets of the data at the moment, more accessible to the science community, but also the general public. And as a last point, which I didn't have time to talk about today, is that I'm working on a lot of new software to basically not only put our data into that, but have like more generic workflows to put different types of data, other models into this platform to provide really like some an open platform to make paleoclimate and also other types of climate data more accessible to the community and the wider public. And if you're interested in this, probably my GitHub is a good point to start. Otherwise, drop me an email. If you're just remotely interested in this or working on similar things, we'd be very happy to talk to you about that. So with this, I'm at the end of the presentation. Thank you very much for your attention. I'm very happy to take any questions. Thank you.
Thanks, Sebastian. Do we have any questions?
Thanks for that, Sebastian. That was great. I just had a question about the land surface characteristics for the for the past climate state. You have paleogeography, topography, and bathymetry. Was the other characteristics like ice cover, was that computed from the model, or was that prescribed by the inputs?
Yeah, this is also prescribed. So like you see some time periods that we have like this yellow line appearing where we have like some ice sheets there, but this is probably talking about all of the uncertainties in paleogeography. Land ice is even more uncertain there. Definitely, so like this really comes is prescribed from reconstruction, mainly based on global sea level reconstruction, and then some sort of like local evidence giving us sometimes a bit of like a spatial shape of these land ice distributions over time. But yeah, we could argue a lot about when to put some ice sheets, where to put them or not. This is totally prescribed, not consistent to the climate that we in the end produce of the models in those models. So yeah, you're right. There's a lot of room to improve on that.
Hi, Seb. Thank you very much. That was a lot of fun. I don't know that it's a good idea for you to advertise that URL halfway through your talk, because I was on an iPad here having a great time watching India smash into the subcontinent. That was really cool. We were just in a breakout session talking about how difficult people were finding it to make paleoclimate configurations for the UM 7.3. Seems like you probably know really well how to make, how to change those configurations to make lots of different paleoclimate UM setups.
Yeah, I mean, at least we have like a lot of experience with doing this in Bristol, because Paul Valdez started this really here and is working on this like for 20 years now. So it's still not something like press play on something and then just putting like a geography in there and then the rest will just be done automatically. It's still some work there, but obviously we have like a lot of help or auxiliary tools that help us doing these things. And at some point now, we basically know which sort of like arrows we can just ignore, which are important basically in the modeling setup there. So yeah, if there's interest in this, we're very happy to share sort of like knowledge that we have. But yeah, we're doing this for like a long time, and it's nice, relatively straightforward to do this with like the old UM with the new UM 10.7, which I'm using for example, like at the Eocene. It's really still like a nightmare. So I can feel your pain there.
Thanks, those are a really great talk, Sebastian. I was just wondering, as well as the visualization for the Climate Archive Dog tool, maybe I missed it, is there a way to actually access the underlying data in those little regions that the user is interested in? Is that part of it?
Yeah, at the moment, so when you specific regions, you can always like just double click anywhere and then you get, then we extract the latitude, longitude of that location that you clicked on, and then we just query, basically wrote like a small API there to just query like our backend. Then we go back to basically actual underlying netCDF data and just do a request on getting temperature, precipitation, for example, of the nearest location, of the nearest time interval that we have data for. And this is then basically added to like sort of like your data card, and then you can download this as like a figure, as like an annual cycle of temperature, precipitation at that location, or you can download as CSV data, for example. Otherwise, all of the underlying netCDF data at the moment is not available from the website itself, but we have all of this on our Bridge website. So the Paleo Group Bridge at University of Bristol, we have like websites where you can access global fields, netCDF files of all of those simulations already for free. And at some point, hopefully, we can merge this. But at the moment, it's sort of like point data you can access from climatearchive.org directly by just double-clicking at the location you're interested in. Or there's a small map icon at the top where you can just drop in like a exact numeric present-day latitude, longitude, and then we do all of the paleo location reconstruction for you. Or you can even drop in like a list of CSV, like a CSV list of locations where you have basically data from, and then we get all of the data that is associated with closest in the model and download this, and then you can use this for further offline calculations, for example. So there's a start, but yeah, we can improve on that.
Perhaps one more from Dietmar, perhaps.
Yeah, Sebastian, great talk and great tool to play around with. I wonder, in your motivation, you showed this 500 million years of CO2 and correlating well with surface temperature. Can you reproduce the surface temperature from your 500 million years with your time slice experiments, or?
Yes, so I mean, GMST, I would say yes, because, I mean, let's say it's, yeah, what's your target? Let's say like, if you put like the three or four different available global GMST reconstructions for the Phanerozoic there, and you plot the GMST curve from our model, which is basically just driven by like a CO2 curve from the Foster et al. Paper, we are within the range of those reconstructions, yes. This is also like shown in the, for example, like in the Valdez 2021 paper, basically we're within that range. it's obviously once you go back to maybe like prior to 300 million years, like the reconstructions, to be honest, are just like so far apart. It's quite easy to hit that because they are so uncertain. But in terms of GMST, we can do this, and we can also get a very good idea about like the drivers there, because we can do like a very easy sort of like first order approximation of the force of the different forcings. So trying to quantify the influence of CO2 changes in vegetation, land sea contrast, or just ice sheets alone, we can build like a very easy linear model out of this and basically simulate the global mean temperature change very well. That's possible, but obviously on a regional scale, like there are all sorts of problems. But yeah, we can do this, and we also do something slightly different sometimes, because sometimes we actually trust like the global mean surface temperature reconstruction a bit more than the actual CO2 reconstruction. So we also have like the same set of simulation where we actually we force this in a way by the GMST curve in a way that we say, okay, we want to reach this global mean surface temperature for a certain time period. We know the climate sensitivity of the model, so this is the CO2 that we put in there, and then we run the same model with those CO2 levels to provide different approaches on reconstructing like the 500 million years of climate change, and we can then hit these GMST curves obviously very, very well, and just try to approach this from like a different direction. But in general, global mean metrics work well.
Great,
Thank you.
thanks.
I guess not too surprising that 500 million years of simulation should inspire lots of questions, but I think we'll have to stop there. So thank you very much, Sebastian.
Thank you.